All right, everybody. So welcome to part two of this section on solutions, acids and bases. Hearty sorry about this goes out to period 4. I gave you the wrong handout today, so you can find the correct handout at the link provided back on my website. So you're going to look for the notes handout for acids and bases. I'll put the link in the description of this video also. So I gave you the problems that we're going to be working on tomorrow in class as opposed to the note handout. So you can go download those notes and print them out and then pick up where we left off. All right. So what we're going to look at today are acids and bases, something that a lot of people are at least somewhat familiar with in terms of they've heard of them. So there's a lot of, you like to use acids in movies, and we looked at them and used them in the Penny Lab, and we saw what they can do. And they can certainly be dangerous and a hazard in the lab, but they're used for a lot of things other than melting things. So they're actually a big industrial component of most of the things we use every day. Started off at one point using an acid to produce. So it's important to know about it. So everyday things that are acidic or bases, well, here's a bunch of pictures. Soda, like our old school Pepsi can there, is an acid. It's actually a mixture of a couple acids. Carbonic acid, which is carbon dioxide dissolved in water, as well as phosphoric acid, pretty nasty stuff. But in soda, it's very low concentration. Vinegar is acidic. Citrus fruits are acidic. A lot of cleaning supplies are basic, and then baking soda is basic as well. So things we might be familiar with. So we're going to use terms that we're going to define first, and those are strong acids and strong bases, as well as weak acids and weak bases. So strong acids are acids that, when dissolved in water, completely dissociate, like those certain soluble ionic compounds, like table salts. So that means if I take hydrochloric acid and mix it with water, all of the H's and all the Cl's are going to separate out and go their separate ways to become H plus ions and Cl minus ions. So if I have a 1 molar solution of HCl, I would have 1 molar solution of hydrogen ions and a 1 molar solution of chloride ions. Weak acids, however, only ionize partially. So if I mix, this is acetic acid, this is vinegar. If I mix vinegar with water, if I make a solution of acetic acid, only a very select few hydrogens, ions, and acetate ions are going to go in a solution. In fact, about 95% of the acetic acid, of the HC2, H3O2, it's going to stay undissociated. They're going to stay together. So the same thing happens when we talk about strong bases. Strong bases, however, are defined by hydroxides, OHs. So usually metal salts from groups 1 and 2, like sodium and potassium and calcium, rubidium. With hydroxides, they form strong bases. So when they dissolve, and sodium hydroxide usually comes to us as a solid, they look like little chips, little white, kind of chalky chips. We dissolve them in water, they completely dissociate to the individual ion. Same with calcium hydroxide. Whereas, oops, I think I went too far. Weak bases only do so partially. One common weak base is ammonia. This is that NH3 that we see on the screen there. And when we mix ammonia with water, only some of the NH3s are going to pick up hydrogen from our water, and that's going to leave water with 1 less hydrogen, and that's where we get that OH on the right-hand side there, right? So our OH is formed by this ammonia taking a hydrogen from water. When it does that, it's going to leave the ammonia with an extra +1 charge and making an ammonium ion, and then the hydroxide, just like we've seen before, has a -1 charge. Anytime we deal with pHs, anytime we deal with acids or bases, we bring up the pH scale. pH essentially is just a measure of the amount of hydrogen ions in solution, and it's a logarithmic scale, meaning every increase in 1 in the scale is an increase or decrease by a factor of 10. So it's kind of like the Richter scale. A 5 on the Richter scale is a 10 times weaker earthquake than a 6 on the Richter scale. So acids on our pH scale are anything in the lower end, so between 7 and 0, with 7 being neutral. And this little diagram is a bunch of things that are acidic. So hydrochloric acid that we used in our lab is very low acidity, very low pH. Lemon juice, also very low. Apples are actually acidic, and vinegar and tomato. And then On the other end, drain cleaner, sometimes called lye, is usually sodium hydroxide. Ammonia is like glass cleaner. Soap is a base. Blood is slightly basic, and that actually depends on where in your body it is. So in muscle tissue, you're producing lots of lactic acid. That's going to make blood slightly acidic. In your lungs, it's going to make it slightly basic. And that's important because hemoglobin, what holds onto the oxygen in your blood, changes shape with the pH of your blood. So in areas that are slightly acidic, the shape of hemoglobin changes such that it makes it easier for it to release oxygen, which is what we'd want in areas that are acidic because you're releasing a lot of energy through respiration. The way we calculate pH is this equation right here. We've got pH is equal to the negative log of the hydrogen ion concentrations. And the way we would do that on our calculator, we would just do negative log and whatever our concentration or molarity of the hydrogen ions are. A couple things to consider. There's such a thing as a pOH, which isn't the negative log of the H+, it's the negative log of the OH-, so it's the base equivalent of the pH scale. Regardless of what the substance is, if I add together the pH and the pOH, I'm always going to get the number 14. And that 14 comes from the fact that water, when we dissolve water in water, as weird as that sounds, when water is just like a glass of water on the table, some of the water actually dissociates into hydrogen ions and hydroxide ions. And when we multiply the concentrations of those two, we always get this number here, 1 times 10 to the negative 14. And this is what we call the KW, or dissociation constant for water. We're going to use these in class to see how we can calculate pHs from concentrations and concentrations from pHs and pHs from OHs and whatnot. So we'll do that tomorrow. Well, depending on when you're listening to this. So strong acids and strong bases, when they react with each other, they tend to neutralize each other. What we have set up here, before we even started talking about acids and bases, we would be familiar with this, and we would see that this is actually a double replacement reaction. So with any double replacement reaction, we're just going to swap out the positive ions for the positive ions. So our hydrogen from over here is going to join up with the hydroxide here. That hydrogen is a +1 charge, hydroxide is a -1 charge. And then our sodium, which is +1, is going to get together with our sulfate. It's going to be drawn as one compound there, and that's a -2 charge. So we crisscross our charges. We put a 2 down here. And to balance this, we're going to need a 2 there and a 2 out in front. Remember, our subscripts don't necessarily come along unless they're part of a polyatomic. Notice here, HOH, that's water. So if I take a strong acid, this is sulfuric acid, and this is a strong base, this is sodium hydroxide. All that I make is a solution of whatever the non-hydrogen cation is and whatever the non-hydroxide anion is in water. So this is a way to neutralize things. One of the uses for this is if you ever get heartburn, that's essentially stomach acid getting up into your esophagus, and it hurts, doesn't feel good. So to get rid of it, you take a base or an antacid, and that neutralizes your stomach acid. All right, so what are the strong acids and what are the strong bases? Well, the strong acids are hydrogen combined with any of these. So bromine, iodine, chlorine, sulfate, nitrate, and chlorate. And the strong bases are the hydroxides, OH added to any of the metals in group 1, except for the hydrogen, because that would just be water, and group 2, with the exception of beryllium and magnesium. So beryllium hydroxide and magnesium hydroxide, they would still be bases, but they wouldn't be strong bases. So this is, unfortunately, you got to know this. This is something you got to memorize. So let's look at the neutralization reaction for hydrogen iodide and sodium hydroxide. So we're going to take our HI plus our sodium hydroxide, and our sodium and our iodine are going to come together. Sodium's a +1, iodine's a -1, so that's the proper formula. And then we're going to take this hydrogen, combine it with this hydroxide, and we're going to make water. and water is just a liquid. So there would be a neutralization reaction. That's how we do that. We're going to introduce a concept of something called titrations, and this is just a way to determine the molarity of a solution that we don't know. So oftentimes they use this, I know for a fact, when making cheese and other dairy products. They got to figure out how much of one ingredient they need to add based on the concentrations of different things in solution. So they'll titrate it out. And titrations use things called indicators. These are basically small amounts of chemicals that change color at specific pH ranges or pH values. So you might be familiar with litmus paper. I think you might have used that in biology or middle school. An endpoint is the place in the titration where the indicator changes color. And the equivalence point is the place in the titration where the number of moles of acid is equal to the moles of base. Oftentimes for titration, we'll try to choose something whose equivalence point is the same as the endpoint. So if we want to have something to have the same concentration of moles of acids and moles of bases, we want to see when that happens, so we'll choose an indicator whose endpoint is right at the equivalence point. So the way it works is we have a concentration of known solution, or I'm sorry, a solution whose concentration is known, and we add it to an unknown concentrated solution to determine its concentration. And we use molarity of our known something to use as a conversion factor. So let's look at an example of this. So I've got a beaker containing 25 milliliters of H2S. We titrate it with 1.50 molar sodium hydroxide. If this process requires 15.65 milliliters of sodium hydroxide, what is the molarity of H2S? So maybe I'm a chemist working in the field, I get a sample of hydrogen sulfide over here. I want to know the concentration there. So what do? Well, first I got to come up with a balanced chemical equation. So I got to figure out the formulas and the parts going in and out. So I've got H2S plus NaOH. And what are we going to make? Well, double replacement reaction. We're going to make water. So by combining those two, and then we're going to make sodium sulfide. Well, sodium's got a +1 charge, and sulfide's got a -2 charge, so we know we need 2 sodiums. And then now we got to balance it, right? So this is the proper formula for water. H2O is what we're familiar with. So I know I need 2 sodiums over here. So I'm going to put a 2 out in front. Now that gives me 2 hydroxides, so I'm going to put a 2 out in front of here. Now I've got 2 hydrogens on both sides, so now we're balanced. So then I'm going to take our volume of sodium hydroxide, and we're going to do that in liters. Since we're going to use molarity as a conversion factor, I know my volumes in molarity units have to be in liters. So I'm going to take my 0.01565 liters, that's right from here, of NaOH. I'm going to convert this essentially to moles of NaOH by using my molarity. So I know 1 liter of this sodium hydroxide solution contains 1.50 moles. Then I'm going to use my balance.
Gilbert, would you please come to the cafeteria? Thank you.
Sorry about that. Then we're going to take our balanced chemical equation and look at the ratio of H2S to NaOH, and I find it's a 1:2 ratio. So for every 2 moles of sodium hydroxide I just have 1 mole of hydrogen sulfide. So this is going to give me, once all my units cancel out, 0.01174 moles. That volume, or that number of moles, is going to be dissolved in 25 milliliters of H2S. So that's going to be 0.02500 liters. We've got to change that to liters. So if I do the math there, I find my molarity is 0.470 big M of H2S. We're going to pause this right here and then go into step 2 because I'm limited to 15 minutes per screencast.